Understanding human safety in HRI is crucial. We introduce FRESHR, a proxemic guided safety framework. It computes the gap between human and robot, subtracts the stopping distance based on relative velocity, and maps it between a minimum safe distance Tmin, 0.46 meter, and a maximum safe distance Tmax, 3.7 meters, which are taken from proxemics. Let's move on to experiment data. In this experiment, we analyze safety from an external observer viewpoint, capturing multiple human movement without occlusions. While robots' onboard sensors provide proprioceptive safety assessments, they are inherently limited by occlusion, sensor range, and field of view constraints. An external observer viewpoint, such as a static overhead camera or another robot, overcomes these challenges by offering a global perspective to the entire human-robot interaction space. Now, looking at the region W and X, respectively, a human suddenly moves toward the robot at a high speed, indicating an intimate zone being breached, causing an immediate GSI drop. However, once the human stops, the GSI stabilizes, demonstrating the framework's real-time responsiveness to velocity changes. Now, in region X, the GSI remains stable despite distant movement in the scene. Unlike traditional models that factor all movement equally, FRESHR prioritizes nearby humans at greater risk. Similarly, in region Y, as the human 3 temporarily leaves, GSI increases, reflecting a safer environment, but when they return at higher velocity, GSI drops immediately, accurately reflecting risk escalations. We have further validated our scale on EPFL crowdbot dataset, which features dense pedestrian flows, varying walking speed, and frequent occlusions. This provided a challenging test bed to evaluate how well GSI can differentiate between different motion planners. Now, we tested 3 different modes: shared control, autonomous MDS, and manual teleoperation. In shared control, GSI maintained the highest safety with an average score of 0.84, showing smooth adaptation to crowd movement and preserving comfortable distances. The autonomous mode GSI averaged around 0.80, performing well overall, but with occasional dips when efficiency led the robot too close to pedestrians. However, the manual mode had the lowest safety, GSI averaging around 0.58, where inconsistent steering sometimes pushed the robot into unsafe proxemic zones. Across these runs, GSI consistently tracked safety fluctuation, dropped when pedestrian came too close, and recovering as the distance increases. Those results demonstrate that GSI not only distinguishes the relative safety of different control strategies, but also adapts reliably to complex multi-human dynamics, confirming its robustness and generalizability beyond controlled experiments. Importantly, these findings show that GSI provides quantitative evidence to compare navigation strategies in real-world conditions. By capturing both average safety levels and moment-to-moment variations, GSI highlights not just which planner is safer overall, but also how each responds under pressure. Thank you.